Today, we're going to have a look at how to fine tune or build a sentence transformer or bioencoder model using a very limited data set. So, when I say limited data set, all we actually need to fine tune this bioencoder model is unstructured text data from our target domain. Okay, so the domain or the area that we want to apply the model to. So the reason that we might want to do this is, I think, quite clear for anyone who has trained sentence transformers bioencoders before. We, in most cases, will find that we don't have that much data, and the data that we do have is usually not in the correct format for actually training a model. So we're going to look at one of the most recent methods for actually doing this, and that is called GenQ. At a very high level, GenQ relies, or the main benefits of GenQ are these 3 points here, or reasons for using GenQ. Our training data is simply unstructured text. So when I say unstructured text, it's if you have, for example, PDF documents or web pages that you're scraping data from, you can use that as your training data. It's specifically for asymmetric semantic search, e.g. where your queries that you're searching with are generally smaller than the passages or context that you're searching for. We'll explain that a little bit more pretty soon. And one of the very impressive things with GenQ is that the performance can approach the performance of models trained using supervised methods. Now, that's not going to be the case for every single use case, and I'd say you're probably going to be relatively lucky if you start getting towards supervised performance, but it does happen. So that's, I think, a pretty good indication that this is a good technique to use, or at least try. So at a high level, let's go through what GenQ actually does. So we start with our unstructured text over here, so our passages of text. We take a T5 model. So a T5 is a model from Google. And the general philosophy of T5 is that every problem in NLP is a text-to-text problem. Okay? And we'll explain that a little more in a moment. But what we're doing with this T5 model is we take our long passages, unstructured text, and use T5 to generate queries, which are these shorter chunks of text over here. Now, these queries are basically questions that the passage should answer. Okay? So what we end up getting are these query passage pairs. Now, if you have trained a lot of bioencoder models, you probably recognize that a query passage pair like this is basically the format we need to actually train a model using multiple negatives ranking loss, which is actually what we do here. So we're synthetically generating these queries, and then we're actually using a supervised training method to train on those queries. So it's almost unsupervised because we are, we're not needing to label data or anything here. But in reality, we are actually labeling data. It's just automated. So it's a bit of a unsupervised/supervised learning technique. And from that, we get our bioencoder or sentence transformer model at the bottom here. Now, don't worry if none of that makes sense yet. We are going to go through everything in a lot more detail. So let's start at the very start with our unlabeled data. We can describe our data as either being in domain or out of domain. So what I mean by that is, for example, we want to train a model that is going to allow us to query or search through German financial documents. Okay, so in domain for that particular use case might be what we have over here. So we have German finance news articles. probably in domain. And then we also have German finance regulation documents, probably in domain. Out of domain, but not too far out of the domain, is English financial documents over here. So in some cases, it can be okay to train your model on some things that are slightly out of domain, like in this sort of area here, if that's all you have. But ideally, you want things to be very specifically in your domain. And then other things like PyTorch documentation. PyTorch, whether it's in German or English, it's out of domain because it's not finance documents. Doom books are definitely sort of getting out of domain here. And even if we had, for example, something like German Pirate Metal, even though it's in German, it's still out of domain because there's probably very little crossover between that and financial documents. So ideally, the data that we do need for training this, it can be unstructured. It can just be documents or web pages, but it should really be within the topic of if we're doing a German financial model, we would ideally want something like the financial news articles or the financial regulations in German. Okay, so that's in domain and out of domain. And GenQ is specifically built for where we have a lot of in-domain data, but it's unstructured, like documents or web pages, as I said before. So another thing that GenQ is very specifically built for is the what I called asymmetric semantic search. Now, asymmetric semantic search is basically where you have asymmetry between the sizes or the length of the text between what you are querying, so your search query, and what you're searching for, e.g. trying to pull from your vector database. Okay, so your queries might be very small. Let's say, on average, they are 32 words long. That's probably actually very long. Your queries are probably even shorter. Imagine what you type into Google, so maybe more like 5 to 10 words at most. And then what you return from Google are pretty usually little chunks of text and web pages and so on. So your passages are kind of like those chunks of text, and they're bigger, right? So there's asymmetry in the sizes between what you are searching with and searching for. That's where you get the asymmetric in asymmetric semantic search from. Now, the next point is that we're synthetically generating queries. So we have that unstructured text, it's just the passages, but to train the model, we're actually going to use a supervised training method. And to train with an unsupervised training method, we need to have queries that match up to those passages. So to generate those queries, we use a T5 model that has been fine-tuned specifically for query generation. So, as I mentioned before, the philosophy of T5 is every problem is a text-to-text problem. So T5 is not just used for query generation. We can use it. We say, okay, translate English to German. That is good. You can get the German translation for that. You can use it for scoring two sentences on how similar they are, and you get like 3.8 for these two because they're relatively similar, and the range there is from 0 to 5. And then you might get a cola sentence. So that is where you are saying, is this sentence correct? Does it make sense? And the course is jumping well, doesn't make sense. So it's saying, okay, this is not acceptable. All of these, although, okay, for example, in the semantic similarity example, we do output 3.8, it's still actually text. So all of this is just text to text. And that's the sort of core philosophy behind T5. It's just an encoder, decoder model. Everything is handled, every problem is handled text to text. The same applies to our problem. We have a passage and we want to generate a query for that passage. Okay, it's just text to text. And with T5, it might look something like this. So the passage up at the top here, we have this really long, this from Wikipedia, and the expert example was on GenQ. It's just a paragraph saying that Python is an interpreted high-level, etc., programming language, and so on. It's just a little intro to Python. T5 takes this and it will say, okay, let's generate 3 queries. Okay, and they're randomized, so it can take this one passage and apply a little bit of randomness and generate different queries. So we get this defined Python program. What is Python program and what is Python used for? Like, they're all queries that we would probably search in Google, for example, and return a passage that looks like this. Okay, now for this we do need a T5 model that has been trained to produce queries, and I'll show you later that we are going to use a specifically trained model for that. And it is worth noting that your queries, or the queries that are generated, can be a little bit noisy, and maybe we'll see an example later of this. What I mean by noisy is that sometimes they can be nonsensical, or I don't know, just weird queries, and like not good quality queries. And that is probably the main issue with GenQ that you need to be aware of, is that because we're generating queries using a language generation model, and that's pretty much the only step in generating the training data. If there's any noise, that will be obviously translated into the performance of our model later on that we are training, and will obviously make the performance less than it could be if the generate queries were all perfect, right? But that's to be expected. Nonetheless, it's, in most cases, I think works pretty well. So let's have a look at an example of this in Python. So here we have the generation code for just one example. So this paragraph here. Okay, so I'm taking this example from the expert.net webpage on GenQ. So all we're doing here is we're downloading a model. We're using a VIA model over here that has been trained specifically for this, although as far as I know, it's been trained for GPL and not GenQ. But nonetheless, this works for this. We initialize a tokenizer and a model using the transformers library here. And we're using T5 for conditional generation, okay, so to generate text. This is our input text, and it's just the same paragraph we saw before. And all we're going to do is we're going to create our input IDs by tokenizing this text. And then we're going to generate 3 sequences here. And down here, all I'm doing is decoding the sentences or sequences that we've generated into text. And I think this is the same example. This is where I actually pulled the example that you saw before from. So we generate these queries, we get define Python program, what is Python used for, what is Python program. Okay, that's all there is to the sort of query generation step. Okay, so not really complicated. We just need to do it for a lot of queries or a lot of passages. Okay, so that's the query generation step, and what we get after the query generation obviously is a set of query passage pairs. And then we can use those to fine-tune our model. Now, for fine-tuning our model, we use multiple native ranking loss. Now, there's sort of a relatively abstract animation going through what MNR is actually doing. So MNR at a high level works by placing all those pairs that we created, the query passage pairs, into batches. Okay, and for each one of these batches, you imagine your query at position 0 should have the highest similarity score with your passage at position 0, because they're the pair, right? But then you have a batch, so you're actually going to compare the similarity between the query at position 0 and the passage at position 1 and 2 and 3 and 4 and so on. And for each batch, the model weights are going to be optimized so that the pair in position 0 have the highest similarity. And for example, query 0 and query 3 or 4 or 5 and so on have a lower similarity, right? And we're not going to go super in depth on MNR here because we've covered it before, and I'll make sure there's a link to that actual article and video in the description. But at a high level, it's basically just a ranking optimization. We are optimizing so that the pairs that should be together, those blocks that you see that are more obvious in the the diagonal line in that batch, those should have the highest similarity scores. Okay, so with that, we will have a bioencoder that has been fine-tuned to our specific use case. Now let's have a look at the actual code that we can use to do that. So the very first step that we'll need to go through is actually getting our data. So to get our data, we're just going to use the squad dataset. The reason I'm using this is because the test set of this has both the questions and context pairs, so we can look or we can assess the quality of our model at the end of this. I'm just checking here. Okay, a lot of these contexts are duplicated because we have, for example, for one context we might have 30 questions. So all we're doing here is removing those duplicates so that we just have the passages. So we can see that the final length or the final number of passages that we have is just under 19,000 here, which is not that many. I think for a lot of use cases, if you're using unstructured data, you can probably get more. But in this case, it does work very well with just a small amount, but it's a very generic data set. So for more specific use cases, maybe you might want to have more data, maybe not. You'll just have to sort of play around with it and see what works. So to generate the queries, you already saw before what we were doing. So all we're doing is loading this model, again, tokenizer and the model. We're setting the model to evaluation. So for example, if there's any normalization layers in there, they are set to their evaluation mode, ready for inference. So just going to shut that. And we move on to the inference step where we are going to generate the queries for our pairs, for our passages. So here, TQDM, we're just using this as a progress bar. There's nothing really fancy going on there. It's just so we can actually see the progress, because it can take a little bit of time, particularly if you have a very large amount of data. We're setting torch to no grad, so we're not calculating the gradients of our model because it takes more time, and we're not updating or optimizing the model. We're just using it for inference here, so we don't need to do that. And then what we need to do is get our passage. So for P in TQDM passages, we are doing that. So if I just show you here, so I'll look at passages 0, just one example. Oh, of course, I'll just have to run this. Okay, and this is just our passage, long chunk of text. So we're going through those. If there's any tab characters, which I generally don't think there are, but maybe there's the odd one, I'm going to replace those because later we're going to be using a tab separated values for a TSV file for storing our pairs. And obviously if we have more than one tab in those pairs separating the query and the passage, it's going to mess up the formatting of the file. So I'm just removing those, placing them in spaces just in case. Then creating the input IDs using tokenizer and code as we did before. Then we're generating 3 queries per passage. We decode the queries to human readable language so we can read it, and so the next model can actually can tokenize that text and understand it. Otherwise, we're using token IDs from another model, which can't be read by our next bioencoder model when we're fine tuning it. So we decode them into human language, and then we are going to add the pairs. So that's our query. Just in case any tab characters end up in there, so we're generating them, we just replace any tab characters with space again. And then we use a tab character to separate the query from our passage. Okay? And then what I'm doing here is I'm saying every 1024 pairs we create, I want to save that or write that to file. Okay? And then we increase the file count, which is because every new file is going to save as pairs. For example, the first one will be pairs 0, and it will be pairs 1 and pairs 2 and so on. Okay? And then we just reset or refresh the pairs list there. Finally, if we, because here we're doing it in batches of 1024, maybe the final batch only has, for example, 600 pairs in there. I'm just saying if pairs is not none, e.g. the list is not empty, I want you to save that final batch. Okay? And with that, we've generated our data. So that's the generative or query generation step. And we can then move on to the actual fine-tuning of the bioencoder model. So to do that, obviously we're in a new notebook now. So first thing I want to do is get a list of all the files, all the pair files that I created before. So that's all we're doing here. We saved it into the data directory, and they're all .tsv files. Then, because we're going to use sentence transformers to train here, we need to import the input example object. And this is just a specific object type used by the sentence transformers library. It's just a standardized format so that we can easily read data that we're going to train with. So all we're doing here is we're looping through all of those files. We're opening all of them, reading all of the lines, so all the pairs. And here, if there's no tab character in the line, we're just kind of avoiding it, just in case, for whatever reason, the tab character isn't in there. And then here, we're splitting, getting the query and the passage, and we're creating the input example. And we're appending that to pairs. So we have this big list of input examples of our queries and passages. Okay? And then we set up the data loader for multiple negative ranking loss. We've done this before, but if you're new to you, obviously we're going to go through it. So I'm using a batch size of 24. With MNR, the greater the batch size, the better, generally, because you're basically making it harder for the model, because if you have more pairs in that batch, the harder it is going to be to rank that one pair that is the correct pair at position number 1. Right, if there's only, for example, 2 in your batch, your model has like a 50-50 chance, if it's just guessing, of ranking the correct pair as position 1. If there's 100 in your batch, it has a pretty small chance of actually guessing that correctly. Okay, so that's why we try and use a larger batch size, but obviously it will depend on the available compute that you have. And then we are going to use this no duplicates data loader from sentence transformers. So this is specifically built to avoid having duplicate queries or context in your queries or passages, in your batch. Because obviously if you're trying to assess or you're trying to rank your query and passages correctly, and you have duplicate passages in there, your model is going to get confused and it can't actually rank them correctly. So we avoid having duplicates in there using this. And then we are just going to define the bioencoder model that we're going to be fine-tuning. So I'm using MPNet model here. MPNet is generally quite good as a sentence transformer bioencoder model, so it's a good one to use. We are using the mean token or mean pooling method here. So all the word embeddings that the model outputs are being compressed into a single sentence embedding by taking the average across all of the dimensions. And we're putting those both together, the actual transform model followed by the pooling layer, to create our bioencoder model. And then after we've initialized our model, we can initialize the MNR loss function. Super easy again with sentence transformers. All we do is losses, multiple negative ranking loss, and then pass the model in there. And then we train. I put single epoch here. We're actually going to train. You can train for a single epoch, or I think that's what they do in the GenQ paper. But I've also seen good results from using 3 epochs here, which is, I think, the default in the sentence transformers documentation. So you go single epoch, maybe try it, see if it works. Otherwise, you go with 3 epochs. In this case, I use 3. Okay, here, ignore that. So we just fit. We pass our loader, loss, like typical sentence transformers training here. And then I saved the model as MPNet GenQ squad. Okay, we warm up for 10% of those training steps as well. And then, the model is saved in that directory, and we can just load it as we would any other sentence transform model. So I think that's it for this walkthrough. What I'm going to do is, in a separate video, we'll have a look at how we can test this model and evaluate it. So that'll be interesting. I'll release it pretty soon after this. So I hope that's been useful. Thank you very much for watching, and I will see you again in the next one.